Hi, we are Cerebros, a group of technology enthusiast engineers representing Alexandria University in Egypt. We have practical experience in several areas, including embedded systems, robotics, and machine learning. We decided to apply this experience in solving one of the problems facing the medical field. Technological developments in the area of brain-machine interface, known as BMI, have received our attention. The motivation for our choice to apply brain control technology to wheelchairs has several reasons. Firstly, the large number of patients who cannot control their wheelchairs by themselves. Amyotrophic lateral sclerosis, brainstem stroke, brain or spinal cord injury, cerebral palsy, muscular dystrophies, multiple sclerosis, and numerous other diseases impair the neural pathways that control muscles or impair the muscles themselves. They affect nearly 2 million people in the United States and 10,000 children every year in Egypt. Secondly, the wide market for wheelchairs and annual market growth rate of wheelchairs, which is 7.6% from 2015 to 2026. Our strategy to add a new feature to these chairs is to enable patients who are completely unable to move to control the chairs through brain signals and enable them to regain some mobility safely and easily indoors, as in home, healthcare, and hospitals. And to move outdoors as well, such as in the streets or any open area with minimal infrastructure modifications. Our brain-computer interface makes use of EEG, which is an affordable, accessible, and non-invasive technique to detect brain activity. For multiple channels headset, motor imagery signals are used to operate the wheelchair by detecting a suppression of the 7 to 13 Hz in the sensory motor cortex, which is the brain area associated with movement when users imagine movements. After successfully being able to control the wheelchair, deploying our own build from scratch deep learning model based on a convolutional neural network, we had to add many safety and monitoring features to the wheelchair in terms of knowing the surrounding environment and avoiding collision. The most common technique used by automotive companies is using short-range sensors like ultrasonic and IMU to detect the stability of the chair, and also a battery management system to check whether the battery needs to be recharged or not. And both of these features can be monitored from the mobile application by the caregiver responsible for the patient. But short-range sensors have a lot of drawbacks and are not reliable enough to guarantee the complete safety of the patient. So we decided to use computer vision in autopilot application using OAK-D. To control the chair, there is a lot of digital signal processing processes and millions of mathematical equations being calculated in real time for the machine learning model. And all of that needed a huge computational power, so adding more models for the vision will cost more computational power and may cause a delay in the performance. The OAK-D camera from OpenCV is a perfect solution for this problem, as it has an onboard processor, which is the Movidius Myriad X visual processing unit that can perform up to 4 trillion operations per second, which is faster for computer vision and AI tasks. 3 OAK-D cameras are used in left, right, and front of the wheelchair to detect any moving vehicle and pedestrians, then locates each object by calculating the distance and angle between the wheelchair and all of the targeted detected objects. And based on all these givens, a priority algorithm will take all necessary precautions in terms of movement of the wheelchair to see whether if it is safe in all directions or if it needs to stop. We also use the camera stream in mapping a localization by determining the coordinates of the wheelchair and putting all surrounding vehicles in Google Maps with a simple technique. When starting the wheelchair, we first get its longitude and latitude coordinates using a GPS measured in degrees. So we calculate the distance and angle of the located object and get the X component and Y component, then convert it to degrees. We wouldn't have finished our project in that great way if it wasn't for our great sponsors. Thanks to them and thanks to OpenCV for their technical support and the offered courses.